Hi everyone, and welcome to our next webinar series with Alplan Bridge 23 version. And in this year, we would like to address your daily challenges when designing bridges with our Alplan Bridge solutions. And in today's webinar, we will going to take a look at free parametric modeling. In the first part, where we will model a small, simple abutment to give you an overview of our new functionalities for free parametric modeling. And in the second part, we will see how we can prepare our project, which is, for example, modeled with free parametric modeling method, and how we can prepare this project with help of global variables to be able to use it as a template for our further projects. Now let's go to the product and let's take a look. So here we have our bridge, which has a slightly curved axis. For this bridge, we have prepared different cross sections, like sidewalk cross section, which we use then further in our main girder cross section as an external boundary, which is referenced on each side. Then we have our pier cross section, and this is already a prepared cross section for our abutment. This is a foundation cross section from the top, and in this cross section we have prepared different reference points. For example, these reference points will be used to reference our piles, and we have also defined different variables, assigned different variables on the parametric lines, which we will use later, where we will move sliders on our prisms. Further, we have a simple wall cross section, a wing wall cross section looking from the side. For our Boolean operation, we have prepared a cross section which we will subtract from our abutment wall. Then on the wing, imagine that here below is a wing wall, and here above we have this small part where we will place then also sidewalk, a cross section for a plate, and a simple round cross section for the piles. Further, we have variation tables for the main girder height. You can see that above the pier, the height of the main girder is the biggest, and we have also a variation for our pier, where you can see that the pier head is slightly wider. Our two structure members, main girder and pier. So for free parametric modeling, in the action bar below 3D modeling, you can find a new function, a new symbol for prism, where you can start this function. Or if you take a look here below on the structure members, we have, like usual, girders, piers, link girders, decks, and the new one, the new category, are also bodies. And with the right click on bodies, we can also start this function with new. The first prism which we will define is the prism for foundation. And we can choose our cross section as we are used, for example, from external boundaries, simply by clicking in the project navigation tree, or when the function starts in the properties window, we have different options, for example, for selecting our cross-section from a drop-down list, and then different options for assigning the geometric position 1 and 2. For example, we can reference our prism on a reference point, which are defined on our main girders and piers and link girders or decks. We can define it between, for example, two docking points, and reference points defined in the cross section are then, when a prism is defined, they become a docking point. We can also use a relative distance or an absolute height. And for the geometric position 2, we have additional possibility to define a relative distance to geometric position 1. So for the first prism, I will choose a reference point and a relative to geometric position 1. So I will choose the reference point at station 2. And further, we can also choose our local direction. We can use the longitudinal direction, the orthogonal direction upwards, transversal left on to the left or right side. And we can also define offsets at the beginning and at the end. So for now, I will simply type in the value of 1.2 meters for the thickness of the foundation. And when we choose the prism, we get our options. In the property windows, we see all the parameters which we have defined. Additionally, we can define also the offsets. And very practical is the position orientation option, where we can simply select how we would like to orient this prism. In our case, we would like to have it oriented in the global Y direction. After recalculating the model, we can see that the prism already has the correct orientation. We can further define the EFC attributes. We can use this prism as a template as well. And all the variables which we have assigned previously in the cross section to our parametric lines, we can see these parameters also here in the properties, where we can also edit them, or these values will change once we use our sliders, which are here represented with brown arrows. When we select the prism, we also get the options of different functionalities which we can use on this prism. Like, for example, we can move this prism, rotate it. And it is very important that all these transformations which are done on the prism are also saved on the list of transformations, which we can then later also edit at any later time point of our planning. We can change the reference origin. We have the list of all docking points. We can move our slider or reset it to the initial values, back to the initial values. We have a possibility to turn on the auxiliary for this prism. We will see later in the modeling process what this is used for. We have, of course, our Boolean operations for union and subtraction. We can also slice our prisms with plane, and we can delete all the Booleans which we have created on this prism, for example. And of course, also all the Boolean operations are saved in a list and can also be edited at a later time point. So first, I would like to move this prism or this foundation below the bridge. So I will choose the function move. And once we start the function, we can choose in our property window if we are moving this prism globally, locally, or from a reference. We can also open or close the degrees of freedom, and we have also different snapping possibilities. We can snap an area of a prism, a mesh point of a prism, or docking points on the prism. So now I will move this prism by a reference. So I will choose this point. I want to go in a vertical direction, and I would like to have this foundation 4 meters below the bridge. So I will simply type in here additional 3 meters and confirm. And now we can see that the prism is placed below the bridge. And further, I would also like to align the edge of the foundation with our second station of the bridge. And for this purpose, I will again use the function move. So I would like to have this point aligned with this point on the bridge. And as mentioned before, I could simply choose my degrees of freedom, or I simply say I want to move this prism for 2 meters in a local y direction, and therefore I will type in for the x and z simply the values 0, confirm the values, and you can see the prism moved only in the local y directions, and it is nicely aligned with the second station as desired and still centered on the bridge. Further, I would like to define the wall, abutment wall. So this will be wall 1. Again, I will choose the desired cross section, and we will define this wall between 2 docking points. This will be the first one and the second one on the other side of the foundation. Further, I would also like to align the upper edge of the wall with the bridge. So I will simply select the slider and snap it to the reference point and confirm the selection, and you see that the bridge is nicely aligned. The wall is nicely aligned with the bridge. To model further walls, I will add our bridge to hidden objects so we can clearly see our abutment. And now I could simply repeat the procedure by starting the function, choosing the cross section and define it, or I can also simply copy wall 1 and say this will be the next one, which will be defined between 2 docking points. It is already there. Of course, we are used from link girders. We are used that we have multiple copy. The same is also with free parametric modeling and prisms. Also here we have this possibility. And when we are copying our prisms, we can decide if we would like to copy the transformations or not. In this case, the transformation done was the change of height. And because I would like to have all 4 walls of the same height, I will copy this transformation. Also for the next wall, we confirm the copy, and then we choose our docking points, and the 4 walls are already created. Further, we would like to have an opening, a door opening here for the inspection of our bearings. Therefore, I will again make another prism. I will again use the wall cross section. We will define this prism between 2 docking points of this wall 1, 1. And we would also like to move doors 20 centimeters away from the wall edge, and we would like to have it a little bit wider, for example 0.8 meters. Now we have created actually a prism in a prism, and to get an opening we will use our function Boolean operator for the subtraction. So we choose the wall where we would like to have the opening. This is the wall 1, 1. Then we choose our subtract Boolean operator and choose the door prism. And now this prism was subtracted from the wall, and now we can turn the auxiliary on, and you can see that the opening is nicely created. If we visualize our bridge again, we see that the bridge, that we would like to have the bridge nicely sitting in the abutment. Therefore, we have to make another subtraction, and for this subtraction we will create another Boolean, another prism called Boolean, and for this prism we will use the extrusion cross section, and we will define it between 2 reference points. Again, we will choose our desired wall, the wall 1, 3. We will subtract this Boolean prism from it, and we will also set the Boolean prism as auxiliary. And let us hide our bridge. And if we click in the empty space, properties open, where we can choose which parts of our bridge we would like to present, and I will turn off the auxiliaries so that we can nicely see how the subtraction was done. Now further, I would like to model a small plate here behind the wall where our bearings will be placed. So for this we will say plate for bearings, and we will again use our wall cross section, which we will define between 2 docking points. So the first one, the second one, and again we will adopt this prism to our desired dimensions. We will use the slider, pardon, this one, wrong one, so this one with, so prism bearings, slider, and this one for the height. As I mentioned before, we can choose, we have different possibilities for snapping. We can snap an area. We can snap a mesh point of this and of another prism, or simply a reference or docking point. But in this case, now we would like to have it in line with the wall. Therefore, I will choose this mesh point, and the plate is already aligned. I would also like to align it with the edge of the doors. So I will choose the slider again and snap to this edge point here. And we have already aligned nicely our plate. Further, we would of course like to model our wing walls of the abutment. So we will first model our wing on the left side. We will choose the wing cross section, and we will choose the geometric position 1 on the docking point with the relative distance to docking point. So I would like to place it here and have the thickness of 0.6 meters. Now we can see that the wing wall is not correctly oriented. Therefore, we will now use the function rotate, and we will first select the rotation axis, then the start. We can move it either manually, or we simply type in the desired rotation angle. And now we have it in the correct position. But let's say that I have used this cross section from some other project and as a template, and I would now like to reuse it. Therefore, I need to adopt its dimensions a little bit. So first I would like to have the height 25 centimeters below the edge of the abutment, upper edge of the abutment wall. Then below, I would like to have it in line with the foundation, and also I would like to have it 5 meters long. So the left wing is already finished, and I will simply copy it to the right side with all its transformations, and I will choose this point as a reference and will move it a little bit to the inside so it sits nicely on the foundation, also on the right side. Further, we would like to model a small part for the sidewalk support on the left side. For this, we will choose the sidewalk support cross section. We will place it between two docking points, and we will copy this support also to the other side with its transformations. So to the right side, from this point to this point, and we will also change a little bit its dimensions. So we will use this slider and snap it to the begin of the first wall, so the sidewalk can run smoothly from bridge to the abutment. The same also on the right side. And now the support is nicely created, and we can place our sidewalk on it. So sidewalk on the left side, we choose again our cross section between two docking points, and we can copy also this one to the right side with all its transformations. And we have also already finished our sidewalks. Further, I would like to model our drag plate. So we will first make a prism for where we will reference the plate. We will place also this one between two docking points. And here we would like to have 1 meter offset from geometrical position 1 and minus 1 meter offset from geometrical position 2. And after recalculating the model, the dimensions have automatically adapted. So now the rest of the plate, we choose our wall cross section for this purpose. Also, this one will be between two docking points. We will change its height. We want to have it snapped here at this point, and we want to also have it a little bit longer, let's say 5 meters. Additionally, we would like to rotate the plate around this axis for the value of 10 degrees. Now we want to finalize our abutment with piles. So we will define the pile 1, choose our desired cross section from the docking point with relative distance, let's say 10 meters. I could also turn off the ground to see it better. And now we will move the pile to the correct position underneath the foundation, and we will use the multiple copy to place the rest of the files to the reference points which we have defined previously in the cross section. So this one and this one, and we can delete this one. So our abutment looks almost finished. Let's see how it fits together with the bridge. Okay, yeah, we can see that the width of the abutment is not completely correct, and therefore I would like to change it and align the sidewalk with the bridge. So for this purpose, I will simply change the width of the foundation prism. I would like to align it to this point. And the left side, the right side is already aligned. The same I will do also on the left side. I will choose the same point as a reference. And also the left side is aligned. And as you can see, all the offsets, all the rest of the prisms moved with the foundation prism, because all the prisms are parametrically connected between each other. Therefore, they all adapt once we change the width of the abutment. Further, I can also see that this wall is a little bit too high. Therefore, I will again hide my bridge and correct the height. And I would like to align it with the top point of this wall where we have done the subtraction. Again, on the other side, I visualize our bridge again. And of course, a model is not finished without a nice concrete texture. And after recalculating the model, we can see our finished abutment very nicely, fitting our bridge. Now let's go to our second part, to global variables and templating. Here we have prepared a bridge which was modeled with these new functionalities, free parametric modeling with bodies. And we have prepared this bridge where we have also defined global variables with which we can now use this project as a template for our further projects. The new possibility in the version 23 is also partial export and import. We can add separate parts of our project to already existing project. And of course, for this purpose, we also need to export our project partially. For this purpose, a TCL subdirectory will be created in which these partial TCLs will be saved, and also another master, so-called master TCL file will be saved, where all these partial TCLs are linked together in a project. Let's take a look how this looks like. For example, this is our folder with all our partial TCLs. And if we take a look at the axis, we see that the axis here is completely the same defined as if we would take a look in a TCL, which is exported as a normally here, as where we export the entire project. For example, if we take a look at this TCL, we see that here we have, for example, at the beginning, we have project settings, materials, and then we see the axis definition. So in these partial TCLs, all these parts which are here saved all together are here saved partially. Further, we have our master TCL. If you export this master TCL, you will see this part where the sources are linked. And if you want to use global variables, this is the place where we set these variables. For example, in this project, we have defined the global variable for the entire bridge length. In this case, this is 60 meters. For the entire bridge width of 40 meters. And below, we have the pier spacing of 15 meters. The pier number will be, the number of piers will be automatically calculated on the basis of the bridge length and the pier spacing. We can also define the relative distance between the piers and the pier height. For the piers, we have defined another TCL where we have only the pier elements saved. We can see here all the prisms, and then here starts the pier counter function where the pier number is automatically calculated and where all the references are also saved. So, as mentioned before, once we prepare nicely our project like this, we can then reuse it in further projects. For example, now we have a 60-meter long bridge with 40-meter width and with 3 piers. Now let's change these variables in our master file. And let's say that our bridge is, for example, 90 meters long. It is, for example, 30 meters wide. And we could leave the same spacing between the piers. We save the changes in the TCL and we re-import our master TCL as usual. Recalculate our project, and we can already see how the entire bridge and all its elements have automatically adapted to the new values. Let's try another variant, for example, 120 meters. And let's say we have the width of, for example, 50 meters with the pier spacing of, for example, 40 meters. We could also change the height of the piers a little bit. For example, let's say we have 60 meters height piers. We save the TCL again. We re-import it. We calculate the model. And we have already our next variation of this bridge model. And we could also try another one where we say a little bit more extremely, and we say, let's say that the bridge is only 15 meters long. Let's say it is 60 meters of width. And in this case now we won't need any piers because the length is much smaller as the pier spacing. We save the TCL, we re-import it again, we calculate the model, and now we have created a small underpass from our initial bridge project. I hope that with these functionalities you could get some new ideas for your bridge projects, and we hope that these new functionalities will help you solving your daily design challenges of the bridges. I would also like to use this opportunity to invite you to our next webinar, where we will take a deeper look in our 3 different methods for modeling: in axis-based modeling method, in link girders, and free parametric modeling, and how these 3 different methods can also be combined in one project. Thank you for your attendance and wish you a nice, pleasant day. We see us at our next webinar. Thank you and goodbye.